Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on February 2nd, 2026, just 4 days ago. It introduces a framework for fine-tuning robot policies entirely within a learned video world model, achieving performance gains of up to 18 times over standard supervised baselines on complex tasks. The paper is titled, World-Gymnast, Training Robots with Reinforcement Learning in a World Model. And as we'll see later, the implications for scaling robot learning without physical risks are really promising. So, Figure 1 maps out the system architecture. On the left, the robot policy receives task instructions and an initial image. It proposes actions, but instead of executing them physically, it sends them to World-Gym in the center. This world model generates imagined video rollouts, shown in the yellow box, which a vision language model evaluates to assign success or failure rewards. These rewards guide policy improvement, and periodically, the system runs real-world evaluations on the right to gather data that refines the world model further. Alright, having seen the architecture, Table 1 compares its real-world performance against Simpler, a standard physics simulator baseline. The results are striking, particularly for the complex manipulation tasks shown in the bottom rows. When putting the eggplant into the sink or basket, World-Gymnast roughly doubles the success rate, reaching up to 78%. It does lag slightly behind on the close the drawer task, but overall, it secures a significant win in 3 out of the 4 test cases. Okay, while the previous comparison focused on simulators, Table 2 benchmarks against 2 supervised learning baselines. The middle columns display success rates for standard supervised fine-tuning, or SFT, and an iterative variant called ITER-SFT. The results for the complex eggplant tasks in the bottom rows are drastic. While the supervised models stay below roughly 20% success, World-Gymnast jumps to over 70%. This massive 18-fold improvement suggests that active reinforcement learning generalizes far better than simply filtering synthetic data. Moving from the success rates to actual behavior, Figure 2 visualizes how these policies handle distractions. The top row shows the standard supervised fine-tuning, baseline failing, and cluttered scenes. On the left, when asked to put the blue cup on the plate, the robot clearly grabs the wrong cup. On the right, attempting to move a carrot, it struggles and picks up a toy dinosaur instead. By comparison, the middle and bottom rows show that both World-Gymnast variants correctly execute the tasks, proving that this method builds robustness against visual noise. Well, having seen those qualitative examples, Table 3 now quantifies how different training strategies impact overall success rates. The baseline supervised fine-tuning starts at 58%. The standard World-Gymnast method jumps significantly to 74%. But interestingly, adding more diversity pushes performance even higher. The distract variant, trained with visual noise, reaches 78%, while adding novel language instructions or scaling the number of tasks boosts success to 81%. So, while the success rates tell one story, Figure 3 visually demonstrates why the world model works so well. The top row, labeled Auto Eval, shows the ground truth, the real robot executing an action sequence. In contrast, the bottom row shows the simpler baseline, where the robot appears as a synthetic gray mesh that clearly clashes with the real background. Between them, the World-Gym Dyna sequence in the second row adheres remarkably closely to the real footage, capturing lighting and textures that the traditional simulator misses entirely. Wrapping up, 2 takeaways stand out. First, World-Gymnast demonstrates that training policies inside a learned video world model can drastically outperform both supervised fine-tuning and traditional physics simulators. Second, by effectively learning from imagined rollouts, this framework paves the way for cloud-based robot training that bypasses the safety risks and costs of physical interaction. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.